Alrighty, I think that's our cue, and I'll just start by welcoming everyone to this ACUR ANU student presentation session. So I'd like to first acknowledge and celebrate the first Australians on whose traditional lands we're meeting. So for me, I'm in Brisbane, so this is the Jagger and Turrbal people, and I recommend you to research and find the country that you're standing on as well. And I'd like to pay my respects to the elders past and present. So my name is Olivia, and I will be chairing today's session. Our first presenter today will be Vincent. And yeah, feel free to start when you're ready, please.
Cool, thank you. Hello everyone, so my name is Vincent. I'm from the University of Sydney in my 4th year of Mechatronics Engineering and Computer Science. Today I'll be talking about efficient 360-degree video streaming with context-based saliency. And just for reference, the picture behind me on the slide is of Venice. And the interesting thing about this picture is that it's a 360-degree video image. So there's quite a bit of distortion, and I'll tell you more about it today. So what's the structure of this presentation? Firstly, I'll introduce the problems faced by current streaming of 360-degree videos, and then I'll talk about some of the motivation behind the research question before outlining the design of my algorithm, and then finishing up with some key results, discussions, and concluding with a few takeaways. So what's the problem that we're talking about? Well, 360-degree videos, which are videos that you can view in all directions, or omnidirectional videos, are becoming increasingly popular. So we see streaming providers such as YouTube, Facebook, streaming 360-degree video content in higher quality and in higher quantity. So this means that there's added increased network pressure in terms of increased bandwidth and increased traffic that these network providers have to deal with. So what's the most popular approach to solving network issues? The current approach is called viewport prediction, which allows streaming providers like Facebook to predict areas of a frame that users are likely to view next. So instead of streaming an entire frame, Facebook can just stream one section of a frame for users, and that reduces bandwidth consumption. However, currently, viewport prediction methods are still data intensive, and this is the main problem that I'm trying to solve today. So let's talk about two main types of viewport prediction. There's trajectory-based viewport prediction, which is about predicting where individual users and groups of users will look in the frame. And there's content-based viewport prediction, which is about showing and highlighting interesting areas in the frame, and then using that to predict where users will likely view next. Now let's talk about the disadvantages behind these current approaches and why this motivates my current research. Well, with trajectory-based approaches, we need to track everyone's data. We need to track where users will be looking around in the frame. And individual users might exhibit volatile behavior. This can reduce accuracy and it can make the prediction algorithm very hard to adapt. Now let's talk about content-based approaches and their disadvantages. Well, content-based approaches, most of them right now focus on images at a pixel level. They don't take into account the context of a scene, the objects in the scene, the relationships between those objects. And there's a lack of research around this area. So there are two key research questions that I aim to address today. Can we use contextual information of a scene to improve saliency prediction? And once the saliency prediction is improved, can we use this to leverage it and use it to improve viewport prediction? So what do we want in the saliency map algorithm? Well, we want 4 key things. We want the algorithm to be content-driven because human attention is largely context-driven as well. We want the algorithm as well to balance different drivers, such as context, motion, and low-level features. And we want the algorithm to exhibit good accuracy and be efficient.
Vincent, Sorry, I might just point out, I'm not sure if your slides are meant to be changing, but they haven't been changing on our screen.
Oh, okay.
Sorry to interrupt that. I've paused your time, but yeah, would you like to, if they are meant to, would you like to try sharing them maybe in presenter mode so that you can show us the slides?
Yes, let me try that. I'm so sorry.
No, that's fine. The technical difficulties are just part of a Zoom webinar. Some presenters do only use one main slide, so I wasn't sure. So if you press F5.
Can you see my changing screen right now? Or is it still, it's still, okay. Is now better? Cool.
Yeah.
Should I start again, or should I just go from where I left off, or?
Judges, do you have an opinion?
For me, maybe just going back and just having a look at the slides that maybe touch on that motivation. So I think where, yeah, around here, just having a quick look at these couple of slides would be good for me. I'm not sure how Barnaby feels.
Got a thumbs up from Barnaby. Yeah.
Cool.
Cool. Yeah, easy.
Thanks so much, Vincent.
No worries at all. So yeah, so the problems I mentioned were 360-degree videos. They're becoming popular. There's more demand around this, and more demand means we're streaming more videos and the video quality is getting higher. So this places pressure on the network. Current approaches talk about viewport prediction. So that's about predicting where users look in a frame. And instead of streaming the entire frame, we stream a segment of the frame where users are likely to view next. But current approaches are very data intensive. And then it talks about, very briefly, like the two types of viewport prediction, where there's trajectory-based prediction and there's content-based prediction. I talked about their advantages, and then I talked about some of the disadvantages. So my current approach right now is content-based prediction, and that focuses on, so current research around the area doesn't consider scene context. The problem I'm addressing is how can we embed our understanding of scene into current approaches. So I talked about like the two research questions, saliency prediction and viewport prediction, and how if we can use saliency prediction, how can we use that to inform and improve on viewport prediction. And then I talked about the four sort of main criterion that we want in a saliency map. Was that an okay summary?
Yeah, that was really great. Thank you, Vincent.
Cool, thank you. So sorry for that, I'll continue right on. So in terms of the algorithm design that we want to have, well, right now we're trying to create an object-based saliency map. So the saliency map needs to be able to identify key objects within the frame, because our hypothesis is that humans are attracted to objects within the frame. Once we've identified the objects, we want to find out the relationships between those objects. And there are two ways of doing this. First, we cluster objects, which means we group objects together based on the semantic similarity. So for example, if there's a computer and there's a computer mouse, we group those two objects together because semantically they're related to each other. Next, we find the unique objects in a scene and objects that really stand out, that are semantically different to other objects in the scene. And we say those semantically different objects are the most salient objects. That informs our saliency map. And then lastly, we apply some post-processing, which pretty much means we apply this filter across the map, we call it smoothing, and that helps us make it go from a discrete distribution to a more continuous distribution, which is more flexible and more effective. And so this diagram shows like a brief overview of the algorithm design. So we have an image input, we detect the objects, we cluster the objects and assign meaning to them, and then finally we smooth the output. So that was talking about the current object-based component. This is the novel component of the design. Then we piggyback on existing motion components and low-level component-based saliency maps, because one of our design criterion of the saliency map was for it to capture all three drivers. We want the map to capture objects, we want it to be able to capture motion, we want it to be able to capture low-level components as well. So now let's talk about some of the key results and discussion points. Well, first we found that saliency prediction increases accuracy after we combine all three maps, after we incorporate object-based information. The second finding we found was that viewport prediction performance is actually quite competitive. It's within the range of other algorithms, and compared to motion and low-level maps, it's very flexible. In terms of our data set, we've performed extensive evaluation. We had over 1,000 frames from 10 videos, each of 1 to 2 minutes long, and each of different genres. So let's look at some of the statistics here. So currently we have saliency prediction, and saliency prediction uses three key metrics: AUC, KL, and CC. We have the higher the AUC score, the better; the lower the KL score, the better; and the higher the CC score, the better. We find that our particular algorithm performs better than traditional methods across all three metrics. And with viewport prediction performance, well, we find that our error is actually quite comparable and within the range of the top state-of-the-art algorithms right now. And if we look at specifically the error in pitch as well, the error in pitch is significantly lower than the other errors of more established algorithms. And while the 68 is slightly higher than the error of other algorithms, it's very much in the range of error. And the key advantage of this particular algorithm is the prediction window. So what does this mean? This means that current trajectory-based algorithms, they can predict where users will look in 3 seconds time, whereas this particular method can predict where users will look in 100 seconds time, or in more extended periods of time. So there's greater flexibility and greater predictive power. So what are our key conclusions here? Well, first, we conclude that content really is key, right? Current methods look at motion, they look at individual pixel level features, but human beings aren't drawn solely by pixels. Human beings are informed by objects, by meanings of objects. And this brings us to our second conclusion, which is if we incorporate object information into saliency map methods, we actually improve predictive performance. And then this improvement in saliency prediction improves viewport prediction, VP, improves viewport prediction, and allows viewport prediction to be more flexible and to predict longer time frames. But this research also raised interesting questions. We found that novel scenes are quite hard. So scenes that aren't traditionally viewed by users, such as scuba diving scenes or roller coaster scenes, those scenes are still quite hard to predict. There's still areas that we need to improve upon. And lastly, we found that this research area is still very much novel. Current methods are very much focused on trajectory-based methods, are focused on pixel-level methods, but this sort of high-level contextual approach, research around this area is still very much needed. And hopefully, this particular piece of research can go into improving our understanding of this field. Thank you, and I'm keen to take any questions.
Yeah, well done. I'm sorry you don't get the in-person experience of an applause, but sorry. Thank you for your presentation and really interesting content. So I'll open it to our judges if they have any questions.
An excellent talk, Vincent. I'm just going to ask something I may have missed throughout.
Yeah, for sure.
So some of my work, I use base perception, algorithms based, actually based on the way the algorithm is constructed, use actual human beings' perception, thousands of them. When you're saying, people care more beyond just the pixels, are the algorithms you're using based on human perceptions, or are they purely constructed?
I might jump in briefly. Barnaby, your microphone was slightly inconsistent. So Vincent, if you heard that, that's fine. But otherwise, perhaps Barnaby, if you could type it or.
Did you hear it, Vincent?
Yeah, I think I only had about 20% of that question. So.
Oh. So are the algorithms you use based at all on human perceptions, or are they purely machine developed?
Yeah, for sure. So I guess a part of this algorithm is that the novel part is it uses psychological research that I didn't quote in this particular presentation, but there was a psychological paper that essentially showed that human beings are very much drawn to objects, and this sort of like object-based relationships, like if a human looks at a mouse, and if a human looks at a computer, they're likely to look at a mouse. If a human looks at a microwave, they're likely to look at the next kitchen appliance. This is all psychological information. It's all psychological evidence. People have done studies around this. And I guess the hope of my research was to really translate the psychological evidence into like a traditional computer vision context. So that's the gap. Psychology is very much focused about high-level drivers, how do humans attach meaning to scenes, whereas computer vision is pretty much focused on discrete units, individual pixel levels.
I'm muted. That would be it. Thank you. Excellent. Chrissy, did you have any questions?
I just wanted to commend you, Vincent. I think you did justice to presenting such like a complex and involved process within your research, like giving us the broad strokes. You actually touched on my main question in your results section, reflecting on how those novel contexts are maybe more difficult to train. So I just maybe wanted to give you an opportunity. Did you want to reflect a little bit more for us around like your data set? Like, did you use a very small, like specific set of those training data to start training your models? Like your example was of Venice. Was that sort of what you focused on and that's what your results were on? Or like, was it a data set that you downloaded that was like a very large pre-existing data set? I might have missed it. It might have outlined in your tables.
Sure. So the data set itself is quite, I guess, quite diverse in the sense that it captures different scenes. But I think the main limitation around not only this data set that I use, but data sets in general, is that there aren't many 360-degree videos out there that are of high quality and that are of different sort of scenes as well. So like if we want to use 360-degree videos in education, there aren't any 360-degree videos about teaching. There aren't 360-degree videos in like the sort of classroom setting, right? So that makes it incredibly hard, pretty much incredibly hard for us to really scale these processes without having the data sets being able to catch up. So currently there is a bottleneck with data sets in the sense that most of the current 360-degree videos, most of them are like very sort of traditional scenes. Like we're talking about roller coaster rides. There's lots of 360-degree content around there. Scuba diving, like travel trips, all of those categories are very much well covered. But if you want to look at and explore more niche concepts or more like real world life concepts, the data set still needs improvement on that particular end.
Great, thank you. That was really interesting insight. And I think it's great to have that critical perspective around the limitations of where your like model was that you were able to talk to. So thank you, Vincent.
Yeah, for sure. Thanks so much.
Yeah, thank you for that. Banwi, did you have any further questions? I guess I just would like to comment again. I think you did deliver that really well, and especially such a complex issue, and to make it so approachable. I hope you enjoyed that, and that
Yeah, it was great.
A useful experience.
Yeah, sure.
As our second presenter hasn't arrived, this brings us to the conclusion of the session. So I just want to let you know that this recording will be made available online following the conference, and hope to see you in other conference sessions this week. And I would like to thank our judges, Dr. Barnaby and Christy. Thank you. Yeah, thank you for your time, and I hope you enjoy the rest of the day.
Thank you so much. Thank you.
Good work.
Yeah, thank you, Vincent.
Okay, well
Thank you.